All right. So welcome to today's lecture. I have entirely lost track. Oh, lecture 15. Perfect. Today we are basically going to stop talking about linear algebra, which is what we've been talking about so far, and we're going to move into a field of mathematics called, you can call it affine algebra or affine geometry is the thing it's most often called. And the point of affine geometry really is to understand things that look like this. So this is my x-axis, this is my y-axis, and I have a line that goes like this. This is a line, I'm going to call it L. So we've learned that subspaces of R2, one-dimensional subspaces of R2 look like lines. There we go. Imagine that goes through 0. Right? So one-dimensional subspaces look like that. So this line L is not a subspace of R2. But like, come on, like these two lines, they're both lines. And we've been learning about linear algebra. It's got line in the name. There's got to be some way we can use the tools we've been talking about to understand these kinds of lines. And this is exactly what we're going to do. We're going to go from linear algebra. Why is it doing this? Sure why my thing is being so problematic. We're going to go from linear to affine. And this transition, linear to affine, is basically going from only being able to talk about lines and planes and other things that pass through 0 to being able to use the same tools we have been using to talk about these sorts of things that don't go through the origin. So let's think of a concrete example real quick. If I have the line y equals 2x plus 3, right? This is going to, it's going to pass through 3, and it's going to have a slope of 2. So it might look like this, barring weirdness with the, oh, of course I'm moving that too. Wonderful. So let's think about this for a bit. If I were to write this equation as y equals 2x with no plus 3, I wonder why this is doing this. It's having these problems. I've never had these problems before. If anyone knows why it's doing this, let me know. So if I were to write y equals 2x, well, I would get a line with the same slope, but going through 0. Right, going through 0, 0. And this, it turns out, would actually be a subspace of R2 because it's a line going through 0. But more accurately, because we can rewrite this as y minus 2x equals 0, which is the same thing as saying, what is it? It's 1 minus 2. Oh, sorry, no, that's incorrect. It's 1 negative 2 times yx equals 0, right? And this is the null space equations that we talked about, right? We have a matrix. In this case, it's this row 1, 2, and it's multiplying by this vector yx, and we're setting that equal to 0 and solving that. And as we discussed, the null space is going to be a subspace of your ambient space, in this case R2. Are there any questions about this so far? Okay, so really what we're doing when we talk about our original problem here is we can do the same rearrangement, but now we have that this is equal to 3. So really the only difference between our linear system and what I'm going to call our affine system is we have this constant here, right? So we could rewrite this whole equation as 1 minus 2 times yx equals 3. And so this is actually, another linear system. It's not going to give, the solutions aren't going to give us a subspace, but it is a linear system, right? And so this is basically our in, so to speak. We've been learning about these linear systems, and now we want to talk about things that are solutions to linear systems, but that are not homogeneous. Are there any questions so far? All right. So we talked about these sorts of systems, right? And the point I made when we were talking about the null space was, if I have some linear system, I'm going to write this in general now. If I have some linear system, AX equals B, and if I know the null space of A, then as long as I have any solution to this problem, right? Say I know AX0 equals, oh wait, no, I need to index that with a superscript. Suppose I know AX0 equals B, right? I told you, but did not prove, that this means that the solution set to our problem is going to look like this. It's going to be the set of all sums, x0 plus x, such that, that's what that bar means, x is in the null space of A, right? So think about what this is. This is just some point, right? And then this here is just another point, another vector here, that's in this space. And when I defined this, I actually said that this, we actually denote this as x0 plus the null space of A, right? So we're basically taking the whole null space of A and shifting it. But if you kind of return to our example earlier, these two lines, right? How did we get these two, this top line from the bottom line? Well, we took the bottom line and we shifted it, right? And so I'm doing exactly the same thing in general. If I know the null space of a matrix, and then I know any solution to the problem, then I can basically get the set of all solutions to that problem by shifting the null space by some value x naught. Are there any questions? Okay. So this is kind of the motivation for what we're going to study, which is we want to describe these solutions to these linear systems that don't go through zero. But before we get into that, I want to take what might seem like a very strange detour. But I promise you it is actually related to what we're doing. And what I want to detour into is this notion of an affine combination. So we talked about linear combinations, right? If I have a list x1 through xk, and these are all going to be vectors in our Rn, all going to be vectors in Rn. A linear combination is just any sum alpha 1 x1 plus dot 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 plus alpha k xk, right? And so these alphas are all going to be scalars. Good to see you, Blame. These alphas are all going to be scalars, right? And so, we just take any linear combination, so any sum of these vectors with any scalar multiple we want, right? And that's called a linear combination. Now, you might wonder, why did we call it a linear combination and not a combination? Why didn't we just say combination? And the answer is that there's more than one type of combination we can take of vectors, and in particular, there's one important one, which is called, which we're going to talk about now, which is called an affine combination. And so an affine combination is actually quite easy to understand, but has a scary name. So it's affine, spelled like this, affine, and then combination. I'm just going to say comb. Okay, so all an affine combination is we take a linear combination, like we were doing, but we're actually going to constrain what these alphas can be, right? So what we're going to end up with is we'll have some x1 through xk again, and we'll have alpha 1 through alpha k. I am alpha 1 through alpha k. It doesn't seem to like my k's. And we're going to take a sum, just like we did normally. So, this is a type of linear combination. But we're going to add another constraint. We're going to require that these sum to 1. Now, we're not going to put any other constraints on them. We're just going to require that they sum to 1, and that's all. But it turns out that this substantially limits the number of possible combinations that you can get, but not by too much. So, for instance, if I gave you, let's say I gave you 2 points, and they're just in two-dimensional space. So I'm just going to draw them, point A and point B. I'm drawing them as circles, but these are points, point A and point B. All right, and we're in two-dimensional space. You could ask, what are all the possible affine combinations that I can get of these 2 points? Are there any questions, by the way? I have my usual pen toolbar. It's just not being shared. So I think it's something weird happening. I'm not sure. But I'll power through. So if I have these 2 points, you could ask, what are all the possible affine combinations I could get? So let's start with some easy ones. Ethan talked about lerp at one point, linear interpolation, right? And so lerp, if you look at it, is actually an affine combination of your point A and your point B. right? Because you're going to have some coefficients, and they're going to sum to 1. So you're going to have some number times the vector A plus some number times the vector B, and those coefficients must add to 1. For lerp, they're also positive, and it turns out that lerp is going to give you the points connecting A and B. And so this is one set of points you can get from affine combinations. But actually, if you allow the alphas to be negative, it turns out that you can just keep going. Going and going and going, going and going and going and going and going. And you can go on forever and ever. And so this line is actually going to be the set of all possible affine combinations of A and B. Right? So basically, you take the line segment between A and B, and you just extend it forever. And that's going to give you all possible affine combinations. Are there any questions about that? I know I haven't proven that. I'll prove it in a bit, but well, I will show an example in a bit. Someone is typing, so I'm going to wait for that. Okay. It seems like there's no questions. The question, okay, so the question in the chat is this how lerp was? Is that how lerp was derived from representing a line from 2 points and using that to interpolate? Yes, basically. So one way of thinking about lerp is you've got alpha A plus beta B, right? And you require alpha and beta to be greater than or equal to 0, and you require alpha plus beta to equal 1. Right? So this is an affine combination, but it is also something more. But the way you can think about it is, if alpha is 0, you're going to have 0 of A contributing to this sum and 1 of B, so you'll end up at B. If you have beta equal to 0, you'll have 0 of beta or B and 1 of A. And so you'll basically end up at A. And in the middle, you're just in the middle. So now, why does affine mean you can use the whole line? Well, if we again think of these affine combinations look like this. If I take beta to be very big, we're going to go more in the direction of beta, right? But then, so if we make beta bigger, we'll go more into the direction of beta. Actually, let me move down a little bit. So we have A, we have B. So we have this line connecting them. Okay. So we can ask, okay, why does taking an affine combination give you this line? Well, let's assume the origin is here at this plus, right? So if I take beta to be big, right? I'm gonna end up out here somewhere, right? If I just take beta times b, right? Because I'm scaling b from the origin. Okay, but I'm requiring that these two things sum to 1. And so basically, if I take beta to be bigger than 1, for instance, right? Because at 1, I'll end up at b, right? If I take beta to be 1. So as I take beta bigger, I'm actually making A negative. So if I kind of like draw the line from A, oh, it really doesn't like that. Like here, by taking taking beta bigger than 0, bigger than 1. By taking beta bigger than 1, I must then take alpha to be negative, which means that this is going to end up, like going out to here or something similar. And so when you add these two, you'll basically end up having to go back onto this line. That's kind of the like visual. It's not like super accurate, but it does work out that way, where basically like if you take one of the numbers bigger, you kind of go off the line, but then the other one gets more negative, which brings you back to the line. So are there any questions about that? I could go through like an actual proof of why this is true, but if people want, do people want to see that? Okay, so I'm going to just talk about the 2D case for now, if that's all right with everyone. Because the higher case, we're not talking about lines anymore. We're talking about higher dimensional things that are hard to visualize. So I'm going to start with the following 2 points. X1, Y1, and X2, Y2. Now, the only constraint I'm going to have is that these are not the same point. Because one thing you'll notice is every time I drew 2 points, I always drew them as different points, right? But if you take A and B, if you take them to be the same point, then any affine combination of them is going to give you back the same point. Because, if you have alpha A plus 1 minus alpha A, this will give you back A, because the alpha will cancel with this alpha, and you'll end up with 1 times A. Okay, so we're just going to require that these 2 points are different. Now they could be they could have the same x value, or they could have the same y value. They just can't have both. Now, how many people know the following definition of a line? So origin plus t times v. So this is like some point plus t times v, or v. So OR and v are both going to be in R2. Do people know this definition? Actually, I'll just show you why it works. So like, what is a line? You've probably learned that a line is y equals mx plus b. But this fails if we have a line that is straight up and down. And this isn't technically straight up and down, but imagine it was straight up and down, right? The slope of this line is infinite, right? So we can't put it in this form. It doesn't work. We need something more general, right? But what we can do is say, okay, pick a point that we're going to start at, say here. Okay, now pick a direction we want to go in, say this direction. Okay, now just take the initial starting point that we've got here and add, basically, like, so we're going to add all the points that go in the same direction as the vector and all the points that go in the opposite direction of the vector. And, barring my squiggly lines, you can kind of see that that's going to be a line, right? So I hope that you'll believe me on that, because I'm going to have to use that in the proof. So does everyone believe me that this gives a line? Or does anyone not believe me that that gives a line? It's kind of more accurate of a question. And note that if I had taken the direction to be straight up, this still works, because I can just go up and I can go down, right? And so these are going to be, this is going to give me the exact same, or this works for any line, even lines that go straight up and down. Are you saying 1 point on the right added to 1 point on the left will make... I'm not sure what you mean by that, Borb. Sorry, so t is in R. T is just a real number. I mean, basically, yeah, like the whole thing is that you start with some point, you go in some direction, and you go all the points in that direction and all the points in the opposite direction. And that's going to give you a line. So let's assume that. Okay, so let's return to our original case, right? We want to talk about these points here. So let's just write it out. What are all the possible affine combinations of those 2 points? Well, it's going to be alpha 1 times x1, y1 plus alpha 2, x2, y2, such that alpha 1 plus alpha 2 equals 1. Well, I can solve for alpha 1, or actually I'll solve for alpha 2, right? This means alpha 2 has got to be equal to it's going to be equal to 1 minus alpha 1, right? So I can just substitute that in here. That's going to give me alpha 1 times x1, y1 plus 1 minus alpha 1 times x2, y2. And so now I've got 2 points and I've got one number that's changing, right? Which is looking an awful lot like my previous example. So let's try and put it in that form of some algebra. Okay, this multiplication here is interesting because this multiplication is going to yield the original vector itself minus alpha 1 times the vector, right? But now we have 2 multiples of alpha 1 in the expression. So we can group them together, and we can get x2, y2, plus alpha 1 times x1 minus x2, comma y1 minus y2. And this is exactly the same form as earlier. This is the original point, and this is going to be the direction. And then alpha 1 here, this is going to be t. So this is going to be the origin of our line, at least. This is going to be t, and then this is going to be our direction v. So it's going to give you a line. It's going to give you a line as long as v isn't 0, right? Because if this was 0, then any number times it will also be 0, and we'll just be left with the origin. Are there any questions? All right. So this brings me to the definition of something called an affine set, or an affine space, as we're going to call it. So we've shown, right, that if you take 2 points in two-dimensional space and you allow for all the affine combination of those 2 points, you will end up with a line. What do you think happens in 3D space when I take the all affine combinations of 3 points? Anyone want to take a guess? Yeah, it's going to give you a plane. And so this is what we call the affine hole, which I know is like a weird word. Affine hole. The way I like to think about it is like the hull of a ship is like the like thing that encloses the ship, right? It's like so like it's kind of like you're talking about like the thing that closes the thing, and then what type of closing are we talking about when we're talking about affine? So we're basically taking all possible affine combinations of a set of points. And so the affine hole of a set of points is just the set of all possible affine combinations of those points. And the affine hole is an example of something called an affine space. So an affine space is, that's not how you say space. You'll see why. An affine space is a set V that's the subset, it's going to be a subset of Rn for some n, and it has the following property, namely that if x1 through xk are in V, so if these are some points in V, then any affine combination of those k points is also going to be inside your space. Do people understand what this means? Basically, I'm saying if you have, so it's some set. This here means contained in, so it's just a set of points in Rn, where if you take any affine combination of points, you're going to get another point that's in your set. So one example of this is a line, right? We showed that if I have 2 points and I take their affine hole, I get a line, right? Well, what happens if I take 2 other points and on this line and take their affine hole? Well, it's going to give you the same line, right? There's no way I could give you a different line, because if I give you any 2 points, you can define a line uniquely, right? So does everyone believe me when I say that like these 2 points will give you the same line as these 2 points? I mean, assuming that they're on the line, of course. And so it turns out this is true for things like planes. This is true for a bunch of things. What we call hyperplanes, which are like planes in the 4th dimension. So yeah, this is the definition of an affine space. And like, affine spaces can be tricky to think about, and they can. And I think the kind of definition that I gave of an affine space is kind of it is correct, but it is potentially difficult to understand, and maybe it's even too difficult to understand. So we can ask, is there an easier way to think of affine spaces? And the answer is yes. Earlier I mentioned, right, that like if you have a line that's going through 0, 0, right, that's going to be a subspace. And then if you want to get another line, what you can do is you can take that. So we have a line that goes through 0. We have a line that is parallel to it but doesn't go through 0. And to get this line, we simply take the first line that goes through 0 and we add a constant to it, right? So it turns out that you can do this with any affine space, which I think is kind of cool, right? Like this intuition that you have about lines, where you can like basically take a line and move it up and down, works for planes too. It works for, hyperplanes and like 100-dimensional generalizations of planes, right? Like all this kind of weird stuff. And it all can basically be written as a linear space, so a subspace, something that we understand, which is like the span of some vectors. Right? So it's a span of some things. And then we just add like a shift to get our affine space. So let's do an example. This is an example we already did, but let's be particular about it. We have the equation, we can look at the equation, like y equals 2x plus 3, right? And this can be written as 2 minus, or, sorry, negative 2 plus 1. I'm changing my variables. No. This is equal to 3. Right, so we can ask, like, what is this space going to be? And the answer is, well, first we have to find some point that solves this to find our shift. And this is going to be, for instance, if we take x to be negative 1, and we take y to be 1, then we're going to get negative 2 times 1 times negative 1, 1. This is going to give 2 plus 1 equals 3. Right, so this is a solution. And so it turns out our whole solution set is going to look like the null space of A plus this column vector negative 1, 1. And if you remember, this is just the set negative 1, 1 plus x, where x is just any thing in the null space of A. And you could compute the null space of A if you want, which it's going to be 2, negative 1, sorry, negative 1, positive 1, x, y equals 0, which implies that y minus 2x equals 0. And oh look, we're back to the equation y equals 2x, right? And so the null space of this is going to look like Well, we sub in, we've got, x, y. We substitute in the equation we have here. We get x 2x, which equals x times 1, 2. And so our whole solution for this line, we can describe the line as the set -1, 1 plus 1, 2 times x, such that x is in R. Yeah. Are there any questions about that? About like how I like wrote out the like set that this plane was, or sorry, that this line was. This is another way of writing this, by the way. But actually, sorry, that's not correct fully. So, yeah. Oh, yeah, are there any questions about anything we've covered so far? I'm kind of, yeah, there's two options. One, everyone is understanding this and everyone's good. And two is I think people are not asking questions because they're not understanding any of it. So are there any, which, okay, fair enough. Yes. So I think probably the best thing to do then would be to end the recording early, and then I can answer more specific questions if that works for people. So I guess I will end the recording.